Welcome back. So now we're going to start talking about some algorithms that we can apply to graphs. And perhaps my favorite such algorithm is called the breadth first search. And the reason why it's my favorite algorithm is it lets me talk about Kevin Bacon and the Kevin Bacon game. So if you haven't heard about this, Kevin Bacon, of course, is a famous actor. And there is a drinking game or a cocktail party game called the Kevin Bacon game, where you pick an actor, Morgan Freeman, and you try to figure out what is the shortest number of movies that these actors have in common through other actors. So for example, if Kevin Bacon starred in a movie with Paul Newman and Paul Newman starred in a movie with Morgan Freeman, then the Kevin Bacon number of Morgan Freeman is 2 because he is 2 steps away from Kevin Bacon. If you starred in a movie with Kevin Bacon yourself, well, good on you. Your Kevin Bacon number is 1. So you can see why this might lend itself to a graph. The nodes in the graph are different actors. The vertices are the movies. And I pick any actor in my graph, and I want to figure out what is the path, the shortest path in this case, to Kevin Bacon. That will be my Kevin Bacon number. By the way, mathematicians play a similar game, but not with Kevin Bacon. They play it with Paul Erdős. So there's something that we all call the Erdős number, which is how many steps away are you from Paul Erdős in terms of publication. So we're going to talk a little bit about breadth first search. And let's do that again with a simple graph here. So I'm going to stick with undirected and unweighted graphs for now. I've got a little graph here with a bunch of nodes, A, B, C, D, etc. And let me start by just defining what a path is in a graph. It's sort of the obvious thing. So if I have a start vertex D right there, and I have an end vertex A right there, then a path between these two vertices is, for example, any way of moving between vertices and obviously along the edges to get from the start to the end. So for example, there is a path from D to B to I to C to A. So think about, for example, if these were cities and I could fly from D to B, B to I to C, and C to A along those edges. That is a path. I can move through the graph legally by jumping between those vertices along the edge. Now, the shortest path, so if I want to get from D to A and I'm not taking my time, I want to get there as efficiently as possible, I might ask, what is the shortest path from D to A? And that's, of course, 1, 2, 3, 4 vertices of length 3. Now, notice this is not unique. I could have also done D, B, E, A. That's also a path of length 3 through 4 vertices. So it's no guarantee that this will be shortest, but that is the length of the shortest path, which is what we're going to be talking about for breadth first search. In this case is 3. So if I want to travel across the country and I want to do that in the shortest possible way, then I might want to ask, what is the shortest path? Now, if these have weights on it, I might ask a different question. I might not ask the shortest, I might ask the cheapest. So if these were the weights were associated with the cost, I might not want to know how many hops. I might want to know what is the least cost associated with it. We're not going to talk about that here. We're only going to talk about the shortest path. All right, so let me just describe some nomenclature. I'm going to describe then the breadth first search algorithm at a high level, and then we're going to dive in and look at the Python implementation, which we're going to have to take a little bit of a sidestep because I have to also talk about stacks and queues in order to implement this breadth first search in Python. But let's first just understand the underlying breadth first search algorithm. Okay, so let me define a few things. I have a start vertex and an end vertex in a, for now, undirected, unweighted graph, vertices and edges connecting the vertices. I would like to know the length of the shortest path and the shortest path, even if it's not unique. So just one of the shortest paths, it doesn't matter which one it is. Let me define, so in this case, let's say the shortest path is D, I, C, A. I'm going to define for every vertex on that shortest path, I'm going to specify the length from the start vertex, so that's 0, 1, 2, 3, and what I call the back pointer. So when I start at D, the length to the start vertex is 0, I'm already there, and there's nowhere to go backwards. Now, if I follow the path, I go to I. The length so far of the path is 1, and the back pointer is D. That is, in order to figure out what the path is, I have to go back to D. Now, from I, the next vertex is C. That has a length of 2 now, plus 1 from the previous one, and the back pointer is I. And then from C I go to A, that length is now 3, and the back pointer is C. So you can see that I'm storing here two pieces of information. What is the incremental length of the path as I move along the path, and then I'm essentially encoding the path here. So once I get to A, I know that how did I get to A? I came from C. How did I get to C? I came from I. How did I get from I? I got to D. And now these back pointers encode for me from A to C to I to D the path of the shortest path that I'm going to derive for. I'm going to show you how we compute it using breadth first search. All right, so here's the basic algorithm. Input is a graph, however you want to represent it. Adjacency list, adjacency matrix, edge list, it's not going to matter now. Now, we are going to obviously have to check if there are edges, but for now, let's not worry about how that's actually implemented. So I give you a graph, I give you a start and an end vertex, and your job is to find for me a shortest path and the length of that path. Okay, so here's how it works. Step 1. Plop yourself down on the first vertex and specify the current length to be 0 and the back pointer to be none because there is nowhere to go. Okay, so this again, the length and the back pointer are going to encode for us the length and the actual path. Now, from that vertex, please visit all vertices that are adjacent to you. That is, please find all of the vertices that are connected through a direct edge and visit them. Okay, so that's I, B, and D. Specify their lengths to be +1 of what you were before, so 0 + 1, and please specify their back pointer to be D. So all I've said is that if I move from D to I, the back pointer from I is D, and that length of that path is 1. If I go from D to B, the length is 1, back pointer is D, and same thing for G. Okay, so imagine sitting at the start vertex and looking at everybody who's connected and taking one step out. One step to I, one step to B, one step to G. What do I know at this point? I know that the shortest path must come through one of those vertices. These are the only vertices that connect directly to D. And however I'm going to get here, I've got to come through this. I can't come through H. There's no way of getting from H to D directly. Okay, so now what I'm going to do, I'm going to start with each of these vertices and I'm going to do the same thing. So from I, I'm going to take a step out to every vertice connected to me. Here it is, wait for it, that you have not previously visited. So from I can get to C and to H and to B and to D. But B and D are previously visited. D was the start vertex and B was visited here. Now, how do I keep track of that? Don't worry about that. We'll deal with that when we write the Python code. For now, let's just visualize it, and I've color-coded them here so you can see. So for every step 2, do the same thing. So for C and H, I'm going to increment the length by 1, so from 1 to 2, and I'm going to set the back pointer to be I. So you can sort of see it now. I can go from D to I, and from I to H. D to I to H, and that length is 2. Okay? Now do the same thing for B. So B is connected to I, I've already seen it. B is connected to D, I already have seen it. B is connected to G, already has seen it. B is connected to E and to F. So I put EF here, increment the length by 1, back pointer is B. G is connected only to D and B, both have been visited. I am done with G. So what have I done? I've started at D, I've taken a step, step, step. For each of those, I've taken one step, one step, one step, making sure not to circle back on myself. So I'm not going to go from D to I to B to D because that kind of cycle is I'm not getting to where I need to get to, which is that A node over here. So you're only allowed to go out a step to visit vertices that you have not previously visited. All right, let's do that step one more time. So for each of the vertices that are on the frontier now, so that's H, C, E, and F, we have to take another step out. We're going to increment the length by 1. That's going to be 3. We're going to count the back pointers, and we're going to do that over and over and over again. So from C, I'm going to visit A. All right, so I increment. So there's my A. I increment by 1. That's 3. Back pointer is C. Now, from H, there's nowhere to go because I've already visited I. From F, there's nowhere to go because these vertices have been visited. And from E, well, I could have gone to A, but I've already visited that with C. So why? Well, I just did it in alphabetical order. So A has now been visited right there. So E, there's nowhere to go. And notice, by the way, let me just cheat a little bit here. Here's the path, D-I-C-A. But if I had gone to A first through E, well, then it would have been D-B-A-A. So it was just the luck of the draw which of these got to A first, and that was just because I did in alphabetical order. So that's where you get the ambiguity of the two shortest paths. Okay, now at this point, every vertex in the graph has been visited. Okay, now I could have said stop when you visit the A, but in that case it would have been the same thing. So we can just go ahead and stop the algorithm now. And now I have everything I want. I have my path D to I to C to A, or if we did it in reverse, here's the final vertice. Back pointer is C. How did I get to C? I. How did I get to I? D. D is the start vertex. And what's the length? Well, it's whatever the length is right there. So to get from D to A was length 3, and now I have two things. I have the actual path, A, C, I, D, and I have the length of the shortest path, which is 3. And you can see now why we call this breadth first search. I started a start vertex and I take one step out in every direction. And then from there I take another one out and another one out. There's a different type of search algorithm called depth first search, where you go deep in one direction versus breadth first search. Okay? All right, so this is the breadth first search algorithm for finding the shortest path between a start vertex and an end vertex in a graph. Okay? So that's the idea. And it's pretty easy conceptually to see that it works, but we have to implement it now, and there's a couple of tricks. We got to be able to find edges. We got to keep track of the fact that edges have been visited. We got to keep track of an intermediate length and the back pointer. So there's a lot of working pieces here, and we got to make sure that we push that frontier forward one step at a time. So to do all of that, we need a new data structure. We need a queue. And so what I'm going to do, I'm going to take a little side step here, and we're going to talk about queues and the related data structure called stacks. Once we know how queues work, we're going to come back and we're going to implement in Python breadth first search. And then we'll do a little bit of runtime complexity on that as well. All right, see you in a few minutes when we come back.